Welcome back to A320 Knowledge, your trusted source for Airbus expertise. Today, we'll be diving into Airbus's guidance on using the weather radar.
As you may know, there are very different types of weather radar systems throughout Airbus fleet. It is of the highest importance that the flight crew understands the system they have on board their aircraft and the way it works in order for them to mentally build a correct image of the weather thanks to what they can see on the ND and sometimes on the VD, vertical display. That is why the first part of this presentation will be dedicated to the different types of weather radars and how they work. But beyond these differences, you will see that we have also some common recommendations on the use of the weather radar. In particular, the fact that there is no health hazard related to the use of the radar. Avoidance decisions and techniques are done the same way for all types of radars. The interpretation of the displays also have very common things to be known. We'll also see that the weather is a very important topic for Airbus now. We have many ongoing projects from short to long term. So, let's start with the different types of radars. The very first type of radars were fully manual, with very few functions. In the 80s, a turbulence function was added. Then, a few years later, a predictive wind shear function. In the beginning of years 2000, auto-tilt radars were developed. Then, a few years later, Honeywell and Rockwell Collins started to work on some concepts of air automatic radars. Rockwell Collins Multiscan, Honeywell RDR 4000, and Honeywell A380 and A350 radars. Let's have a look at these different types of radars and the way they work. The manual radars only display a slice of weather for a single tilt angle. They are fully manual. There is no default value for the tilt. The beam is 3.5 degrees wide, so it means that the slice of weather increases with the distance. With such manual radars, the tilt has to be manually adjusted to find and to correctly see the weather. For example, here with the first tilt value, you will see only the top of the cloud. You will have to adjust the tilt to down in order to see the core of the cell. That is why, for aircraft fitted with manual radars, we recommend to perform a periodical scan of the entire space. Then, when the weather scan is completed, adjust the tilt so that the ground returns appear on the top of the ND. All of these techniques are provided in our Flight Crew Technique Manual in the section Aircraft Systems Weather Radar. And this is the case and will be the case for all types of radars. Now, let's move to auto-tilt radars. Auto-tilt radars display also a unique slice of weather for a single tilt angle, a little bit like the manual radar. But the difference with manual radar is that in auto mode they provide a default tilt value, which is an optimized value as a function of ND range, aircraft position, altitude, and terrain database. With auto-tilt radars, the tilt auto mode is the default mode. However, manual tilt is still necessary for further storm cells analysis and also regularly to enhance weather awareness. We can say that manual and auto-tilt radars are very similar in terms of operation, even if auto-tilts provide the possibility to have a default value that is very useful. Let's move now to the first type of automatic radar, which is the Rockwell-Collins multiscan. With this radar, there are two radar beams corresponding to two tilt values superimposed on the ND, the lower beam and the upper beam. Tilt and gain are automatically adjusted based on aircraft position, altitude, terrain, time and season. Recently, Rockwell Collins has developed a V2 version of the multiscan radar with new functions, hail and lightning detection. With the multiscan, you have to use the manual tilt in order to display a single beam and to distinguish what comes from the upper beam to what comes from the lower beam. This is very important to be able to make a mental image of the real shape of the cell. Let's move now to the second type of automatic radar, the Honeywell RDR 4000. This radar has a very different philosophy in comparison to other types of radars. It performs a continuous scan of the space in front of the aircraft, and then the Honeywell RDR 4000 totally rebuilds a model of the weather in 3D. This model is stored in a buffer. Then the radar flattens the 3D buffer relevant features on the 2D ND. It means that the image that you have on the ND represents in fact the worst weather for all flight levels. In order for the pilot to be able to distinguish what is vertically close to the aircraft from what is more far away, the RDR 4000 uses a logic of on-pass, off-pass. It means that all the weather that is located at aircraft altitude plus or minus 4,000 feet, with a minimum of flight level 250 in cruise and 100 in takeoff and landing, is considered as on-pass. The weather that is outside this path is considered as off-pass, and so is displayed hatched on the ND. What is also new with the Honeywell RDR 4000 is the possibility to have two different displays on captain and first officer sides. As explained before, the 3D buffer enables to display more weather than only the one of the current flight level. In auto mode, it's a little bit like if you had a superimposition of the weather for all flight levels on the ND. That is why it is very useful to use the elevation mode to analyze the precise structure, vertically speaking, of the cell on the ND. With the elevation mode, you do some horizontal cuts along the FMS flight plan. In the following example, if you use auto mode, you will see the whole cells and you will see red, yellow and green areas on the ND. If you perform a cut at flight level 250, you will see only the top of the cell. If you perform a cut at flight level 100, you will see the core of the cell. Let's move now to A380 and A350 radars. These radars were developed by Honeywell and have the same principle as Radar 4000. A 3D buffer, on-pass and off-pass displays, and the possibility to display two different images on captain and first officer sides. On A380 and 350 aircraft, the radar is embedded into the Aircraft Environmental Surveillance System, AESS. The very big difference for this aircraft does not come from the radar itself, but from the fact that the vertical display is available in the cockpit. With the vertical display, you have a direct image of the vertical structure of the cell along the flight path. As a result, the elevation mode can still be used, but it is only for precise analysis of the structure of the cell. On A380 and A350 radars, there is also another function which is called azimuth. Azimuth mode enables to display a vertical cut along a specified azimuth. For example here, along the flight plan, you can see that there is a red cell. If you try to see on this azimuth, you will see that you're only on the green, and that it is also the case vertically speaking on the end, on the VD. Let's now have a look at the fleet status regarding these different types of radars. On A320 family, you can see that nearly half of the aircraft are equipped with automatic radars. Auto tilt represents 12% of the fleet, and manual radars are still present in 40% of the aircraft. It is more or less the same repartition for A330 and 40 families. A little bit more automatic radars, 57%, 12% of auto tilt, and 31% of manual radars. A380 and A350 aircraft are all equipped with the Honeywell dedicated radar, meaning that they all have 100% of automatic radars. As you can see here, on A320, 30 and 40 families, it is possible to have different types of radars, and even inside the same fleet of one single operators, you may have different types of radars. So, on these families, you may face mixed fleet flying in terms of weather radar systems. How can the flight crew know which radar is on board the aircraft? Well, everything relies on the panels. If there is a tilt rotary knob, it is a manual radar. If the tilt has a man and auto function, it is an auto tilt radar. If you see multiscan written on the top of the panel, of course it is multiscan. Eventually, if you got the possibility to display differently a captain and a first officer side, it is a RDR 4000. But as said in introduction, even if there are different types of weather radars and different uses, there are also, beyond these differences, some common recommendations. First, regarding the use of the weather radar. We have recently updated all our SOPs, all programs, in order to emphasize that the radar should be set to on before takeoff, in order not to omit it later on in the flight, in particular if the weather is good during the takeoff. Then, we would like to take the opportunity of these seminars to confirm that there is no risk for pilot's health in using the radar. Our radars are compliant with the only regulatory circular that exists, which is the FAA AC 2068B. It means that the area for emission, maximum emission of the radar, is only located 6 centimeters behind the antenna, which is very far from the cockpit. In addition, the cockpit works as a Faraday cage. So, the emissions is very, very low in the cockpit for the radar. In addition, we have new operational recommendations in FCTM for all programs. Regarding avoidance decision, it is no longer linked to the height of the cells, and it does not rely only on colors. We have recently introduced in the FCTM the notion of area of greatest threat. This area of greatest threat is based on the location and shape of the strongest weather radar echoes, but is also based on the meteorological knowledge of the flight crew. It is, in fact, the zone where the flight crew estimates that the weather conditions are too dangerous to fly in. As you can see, it really empowers the crew's expertise. Because all of you are used to fly in different areas of the world and know the weather and know the different possibilities and the different dangerosities of weather, depending on the area, depending on the day, etc. We also have some recommendations about the avoidance technique. The margins, you have to take margins, but these margins are now around the area of greatest threat, 20 nautical miles laterally, 5,000 feet vertically. We also recommend to increase the margin if the cloud is very dynamic. What is still applicable is the need to analyze the weather in detail and to make a correct mental image of the weather in your brain. We also recommend to prefer upwind and lateral avoidance, which is the safest for the aircraft. Regarding the ND range, it's interesting to use low ND range because the radar is more precise. But with such a low range, you can have what we call the blind alley effect, which is the fact that you miss weather that is a little bit more far away than the selected range. High ND ranges, despite lower precision, are very interesting to avoid the blind alley effect. That is why we recommend to combine two different ND ranges on the two sides of the aircraft at the same time, in order to take the advantages of both low and high ND ranges. Regarding the shapes, analyze shapes combined to colors, and not only colors. For example, in the finger, hook, or U shape, these black areas may become very quickly red because the finger or the hook or the U may close on itself very quickly and build a very dangerous area of weather. Another example, for closely spaced, you see that the red is very close from the edges, so this may become red very quickly. Regarding the gain, using manual gain can be interesting to detect the weather. If you reduce the gain, you will be able to identify the zones with the highest precipitation. If you increase the gain, you will improve long-term accuracy, and so you will be able to perform a deeper analysis of a cell. We also recall you that black holes located behind red areas are often very active. They are what we call storm shadows. So, these black holes should be totally avoided, even if displayed in black on the ND. Note that there are some enhancements that were implemented recently in Multiscan and RDR 4000 V2 radars. Now, please let me remind you a few tips for the tilt. First, what we call the 160 rule of thumb. If you have a tilt angle of 1 degree, it means that at 40 nautical miles, you look 4,000 feet below the aircraft, and at 60 nautical miles, you look 5,000 feet below the aircraft. Also remember that the tilt angle of 0 degrees means that the radar beam is referenced to the horizon and not to the horizontal axis of the airplane. Let's move now to an overview of Airbus project regarding the weather. First, the weather on board. The weather on board project is to be able to display weather information and weather forecasts directly in the aircraft through EFB. It is a very useful strategic tool in order to anticipate things before the weather radar's range. The weather onboard application is already being deployed on some aircraft today. For example, it provides lightning observations, SIGMET forecasts, clear air turbulence and winds forecasts, CB-TOPS forecasts and satellite observations. Another project that we have in Airbus is what we call the aircraft as a weather sensor. This is a mid-term project. The aim is to use all aircraft as meteorological balloons that could be able to sense different weather conditions, turbulences, temperatures, ice crystals, winds, etc. Then the aircraft could send this information down to the ground, and then this could be reused by other aircraft or by the ground. This project was also presented during the Airbus Flight Safety Conference in Santiago soon this year, and is closely in relation with the Destination 10X project launched by our Airbus Safety Department. We also have some areas of research. It is on the long term. For example, the fusion of radar and uplink data, or a 3D weather analysis and automatic rerouting of aircraft. I would like to take the opportunity of this presentation to make a small spot on ice crystal. Well, today it is not possible to detect ice crystal with existing radars because they have a too low reflectivity. We have, however, created a new FCTM chapter to explain the phenomenon of ice crystals. Ice crystal icing is always located above or downwind convective clouds. That is why classical radar operational recommendations are useful. These recommendations say to prefer lateral and upwind deviation. By doing so, you will also avoid ice crystal areas. Then we give in the FCTM some clues to identify ice crystals. Appearance of rain at very low temperature, surprising TAT around 0 degree, etc. The FCTM also recalls the good practices in the case of an event because of ice crystal. We only recommend to follow Airbus sensed and not sensed procedures, such as engine failure, engine relight in flight, unreliable airspeed, etc. But we also work in parallel on ice crystals detection, and this is a mid-term project. As you may know, there is an international collaboration since 2004 in order to work on ice crystals. Airbus has participated to this collaboration and has performed some tests in icing wind tunnels and also some flight tests. As an example, there were 3 campaigns of 26 flights in very deep convective clouds. We have also developed a specific instrumentation for these flights. The outcomes that will come in the coming months or years are ice crystals detectors and the possibility to get enhanced weather radars that will detect ice crystals. As a conclusion, we can say that it is very important that the flight crews know his radar. What does the display represent? Is it one or several slices? It is the superimposition of two beams? Or is it the 3D flattening of a buffer? Then, depending on what you have to use manual gainer modes in order to better assess and understand the situation. Once again, it is the mental image of the weather that you will make in your own brain that will be the way to decide if you avoid or not a situation. Then, apply operational recommendations. Use your weather knowledge in addition to the radar. You are used to fly in some areas of the world. You know how the weather becomes, if it is in summer or winter, if it is hot or cold in such areas. Use all clues and not only colors, shapes, cell dynamism, lightning, etc. Use recommended avoidance margins and methods, upwind and lateral deviation, for example. Then, talk and train by experience. Encourage experience sharing within your crews. Also, during the seminar, we'll have some training roundtables where you can talk about training experience on the radar. Eventually, we remind you that weather is an important concern for Airbus and that we have many ongoing and future projects on this topic. Thank you for your attention.
Our popular A320 tech quizzes are now part of an exclusive newsletter membership designed to provide you with even more value. As a member, you'll receive 4 brand new A320 tech quizzes every month, one each Monday, delivered straight to your inbox. You'll also receive exclusive deep dives into A320 systems, procedures, and techniques that go beyond this YouTube content. And you'll also gain access to bonus content and other surprises to keep your knowledge fresh and up to date. If you're interested, click the link in the description or scan the QR code on screen to sign up today. Thanks for tuning in, and let's take your A320 knowledge to the next level.